Hi, welcome to the video solution for Edexcel Physics. This is IAL Physics Unit 2, January 2019, Part 2. So let's start. Question number 12. The diagram shows a potentiometer. It consists of a track made from carbon. The resistance between terminal A and the terminal C is equal to 47,000 ohm. So this is A and this is the track from A to C, and the resistance of this track is 47,000. A sliding contact moves around the track, is connected to the terminal B. This is sliding contact, terminal B. The carbon track has a uniform rectangular cross-sectional area. Calculate the thickness of the carbon track. Length of the carbon track is 2.7. Width of the carbon track 3.0 millimeter, and resistivity of carbon is 2.5 times the power minus 5 ohm meter. So if you see the cross-sectional area of this track is a rectangular, something like this, and they have given us the length of the track, the total length, and the width means we have this. This is the width, and we need to find the thickness. I'm just going to call it T. And it's not that difficult because we know that length, resistivity, and the resistance are given. R and the length and rho is given. And if we can find the area of the this track using the resistivity formula, so we can figure out the thickness. That's what we are going to do. So we know that the resistivity of a material rho is equal to R area by length. That means area is equal to resistivity times L divided by R. And if you substitute the value, rho is 2.5 into 10 to the power minus 5. And the length is 2.7 into 10 to the power minus 2 divided by resistance is 47 kilo ohm or 47,000 ohm. So area we are going to find is 1.44 I guess into 10 to the power minus 11 meter square, and this is the area. And if you divide area with the width, which is given, so we can have a thickness T. So thickness T is area divided by the width. But remember, the width is in millimeter, so you must convert this millimeter into meter. So if you divide area, which is 1.4 into 10 to the power 1.4 into 10 to the power minus 11 divided by the width. Width is 3 into 10 to the power minus 3. So thickness will be 4.78 into 10 to the power minus 9 meter, or you round it off till 4.8 into 10 to the power minus 9 meter, or nanometer if you wish to say. So this is your thickness. Part B, the potentiometer can be connected to a 9-volt supply to provide a variable output for a buzzer as shown. Explain how this circuit provides the variable output for the buzzer. The current drawn by the buzzer is negligible. Clearly, if you see that the buzzer is in parallel with this potentiometer, so this is a potentiometer. In fact, you can see this as a rheostat, or maybe, of course, the variable resistor. But we have a 3-terminal. This is, if you recall, in your laboratory, you have used a rheostat, and in the rheostat we have a cylinder, and we have a wire wound here, like these. So now this is a potential divider circuit, and the potential of buzzer will be equal to potential between B and C, because you know that these wires or this region is parallel to the buzzer. So whatever the potential of BC is, potential of the buzzer will be same. Now if you move slider closer to C like that, so what is happening? Length of the wire is decreasing, so the resistance is decreasing, and the potential between B and C is also decreasing until you reaches potential of 0. So if B is connected with the C, then the potential difference between the point or for the buzzer will be 0. And if you move towards A, then the potential difference keeps increasing and increasing and increasing, and at A the potential difference will be maximum. So that's how you can vary the potential between the point B and C or around the buzzer if you slide the slider B along AC. So you can include all these points in the statement like that. I hope you will be understanding all these points. So the given circuit is a potential divider, and the potential divider across the buzzer depends on the position of the terminal, where the B is. And if B moves to C, then potential difference is decreasing until it reaches at C, where potential difference is 0. And if B moves towards A, then the potential of B or buzzer will be increasing until maximum at A. Question number 13. Helium was discovered in the 1860s by observing the spectrum produced by sunlight. An intense spectral line was seen which did not correspond with any elements known at that time. Explain how specific spectral lines are produced by hot gases. Again, it is a typical question of Unit 2 about energy levels and excited state, emitting and absorbing electron and energies. So the conclusion of all these explanation is, you know that in atom, if this is the nucleus of the atom and we have orbit or the energy level around a nucleus, and we call these energy levels as discrete energy level. So atom has discrete energy level of E1 and E2 and E3. Every level has its own specific energy. So when electron stays in any one of the energy level, it revolves with the same energy. If the atom absorbs energy from outside, suppose this is the energy absorbed by the atom from outside, then the effect of this absorbed energy is the electron in the atom jumps to the higher energy level due to increase of the energy, and the atom becomes excited. And after a while, the electron jumps to the lower energy level, maybe the same one or maybe the other one, depends on the nature of the element. So when atom absorbs energy, the electron goes to the higher energy level, and later on the electron goes back to the normal state or the ground state and come back to the lower energy level, and then in this case it releases energy. This is the released energy, and this released energy is in fact depends upon the difference of the energy levels of the two transition. So when electron is coming back, it is releasing energy, or a photon of energy delta E, which is the difference of the energy of the two, and there are specific lines. That's why we have a specific spectral line, because every element has a specific energy difference or its own unique energies level in every atom. So you can combine all these points like that, and this is a typical answer for these types of question. Whenever they give you the word getting spectrum absorb energy, or spectral lines, emission and absorption spectrum, so you can include all these points in your answer. Question number 14. Refractometer can be used to measure the refractive index. A refractometer make use the total internal reflection of light at the boundary between the two materials. Describe the condition required for the total internal reflection to took place at the boundary. So for total internal reflection, TIR. So for total internal reflection, we have two important conditions. Number one, the first condition is refraction should be from dense medium or from denser material, more dense material, or you can say medium, from more dense to less dense. So refraction should be from more dense medium to less dense medium. This is the first condition. And then the second condition is the incident angle should be greater than the critical angle. Then we can observe total internal reflection. You can use from high refractive index medium to low refractive index medium, like water to air or glass to air or glass to water. These are some examples of refraction from denser medium to rare medium, or from high refractive index to low refractive index. And if the correct incident angle is greater than critical angle, then we can have total internal reflection. One type of refractometer is shown. A sample of liquid is placed on one side of a semicircular glass prism. A ray of light is shown passing into a prism. Okay, determine whether this ray will be totally internally reflected from the boundary between the prism and the liquid. So the refractive index from liquid to glass is equal to 1.15. So if you know that you are given, this is glass, high refractive index, and this is a sample of a liquid, low refractive index, you need to find whether you can observe the total internal reflection or not, like whether we can have these kinds of situation or not. So we have first condition, most probably, that from we have a refraction from denser to rare. But the second condition, we need to check whether this incident angle is greater than critical or not. So the easiest way to determine this, we can if we can manage to find the critical angle of this situation. So you know that the critical angle sine C is equal to 1 upon n, and n is refractive index, which is 1.15. In this question they used mu for the symbol of refractive index. I'm using n, it's fine, it's just a formula. You can use 1 upon mu, so it's just a symbol, and you can figure out C here. So C is equal to sine inverse 1 upon mu, and mu is 1.15. If you calculate, then C is equal to 60.4 degree. That means the incident angle is less than the critical angle. So we cannot observe this total internal reflection. You don't need to mention this diagram. I just showed you for your understanding. But this is the important conclusion, that incident angle is less than the critical angle. So we cannot have a total internal reflection here. Part C, the graph shows how the refractive index mu varies with the mass of the sugar dissolved in a fixed volume of water. This is the graph. So on y-axis we have a refractive index from sugar solution to glass, and then on x-axis we have a mass of the sugar. So explain why the critical angle would have to be measured to precision of more than 2 significant figures in order to determine the sugar content to nearest gram. So why we should use or measure critical angle more than 2 significant figures? The reason is, if you see the graph, first of all, you can see that the refractive index is measured throughout the graph. Refractive index is measured more than 2 significant figures. So you can see that you have 1.104 and so on. So you have more than 2 significant figures measurement. But more importantly, if you see, suppose if we use just 2 significant figures, suppose if we use just 2 significant figures, and if you see here, from this to this, so we have variation of mass. From here, the mass is continuously increasing. Okay, mass is increasing, but if we are using just 2 significant figures, so 1.10, 1.10, 1.10, that means in case of 2 significant figures, there is no change in refractive index. So we have a change of the mass around 40 to approximately 20 gram. So 14 to 20 gram, we are changing mass around 6 gram. We have changed, but there's no change in refractive index if we use just 2 significant figures like 1.10 or like that. If we use just these 2 SF or 2 decimal place, then we cannot determine the change in refractive index. So we will have to use at least 3 decimal place or more than 2 significant figures like that. Question number 15. Scientists have succeeded in levitating droplet of liquid. A standing wave is created using ultrasound, okay, generated by 2 sources, one above and one below the liquid. The droplets of liquids are trapped at the position corresponding to nodes as shown. Okay, explain how standing wave is formed. So a standing wave is formed when 2 coherent waves moving in opposite direction. So one wave is coming from left and the other wave is coming from right, like this. So 2 waves traveling in opposite direction, when they interact or they superpose, they produce pattern of maxima and minima, or pattern of constructive and destructive interference, or you can say nodes and antinodes. That can be described as a standing waves. So 2 coherent waves traveling opposite direction interact or superpose to produce pattern of maxima and minima. Describe the motion of the air at nodes and at antinode. So if you see that it is all about standing waves. So a standing wave is kind of something like this. So these are nodes, and these positions are antinode. So basically the standing wave is a vibration. So all the particles in the standing waves are oscillating up and down so quickly, like this. So if this is a particle of a medium, it is oscillating up and down so quickly, and the particle A, which is at antinode, is also oscillating. So but at node there is no oscillation at all. So the air particles at node are not oscillating or at rest, while particles at antinode, they are oscillating with maximum amplitude. And moreover, this is the formation due to ultrasound, and the oscillation is parallel to the direction of motion of wave because of the sound wave, which is a longitudinal waves. So you will have to include all these points because it is 3 marks. So you will have to say about the node, antinode, and oscillation of the longitudinal waves. So you can write all these points. Part C, the scale of photograph is half full size. Determine the frequency of the ultrasound wave. Speed of ultrasound in air is 320 meters per second. Because it's all about, they are saying that the scale of the photograph is half full size. That means you will have to take measurement from your photograph. Your photograph is a scaled photograph. So in this question on this computer, I cannot show you this the actual size, but suppose this is the picture in your question paper, and I am assuming that this is a scale photograph. The meaning of half full sized mean whatever measurement you are taking from the picture, it should be double of the measurement. The actual measurement will be double. So you can say that if you are suppose if they ask you to measure the length of the stand, actual length of the stand, so you will use your ruler and you will do the measurement from your meter rule or your normal ruler. Whatever the measurement you get from your picture, you will have to multiply this measurement with 2 to get actual measurement of the stand. That's the meaning of half full size. So you will have to determine the frequency of the ultrasound wave. So it's all about formation of standing waves. And you know that if you need to find the frequency, you will have to use formula V is equal to F lambda. And F is the frequency needed to be found. V is given. We need to figure out wavelength from the measurement taken from the photograph. So you know that these dots are showing position of nodes. That means if you see, you have formation of one loop here, something like this. So I am showing you the a diagram, something like this. That's what is happening here. So this is your particle number 1, this one, particle number 2, which is there, particle number 3 is here, this is particle number 4, and so on. So you can take measurement, and it's not good idea to take measurement just for 2 particles because it is a very small length. So excuse me, it will be good idea if you include maximum number of particles. So you can take all, or you can take 4 or 3. 3 will be sufficient, or 4 or 5 will be good. So I'm using for 6 position, for 6 droplet here. If I use for 6 droplet or for 6 point, so for 6 point, if I take measurement, if I took measurement for the 6 point, I have measurement around 11.6 millimeter. That means for one loop, that means if I have a 6 loop here, you know that 6 droplet means 6 loops. If I need to take the measurement only 1, so 11.6 divided by 6 is going to give me 1.9 millimeter. So this is the length of one loop, and Of course, for a scale diagram, I have to multiply the measurement with the 2. So actual length of the one loop is 2 times of 1.9. So the actual length of the loop L is 2 times of 1.9 millimeter, and then I have the length is 3.8 millimeter. So now I have a length of one loop, and we know that for one loop from node to another node, this length in terms of wavelength is lambda by 2. So you can say that lambda by 2 is 3.8 millimeter. And then lambda would be equal to 7.6 millimeter. This is the wavelength that we found. And now you can use this lambda in your formula. Be careful about the millimeter. Don't forget to change millimeter into meter, okay? And then you can use 7.6 10 to the power minus 3 in place of wavelength and times and divided the velocity. So you can have a frequency is F is equal to 41700 hertz. So this is it's better to write hertz, something like this. This is hertz. That's how you can figure out the frequency of these standing waves here. Thank you very much for this video. I hope you enjoyed it. See you in the next one. Have a nice time.